Hi all, welcome to my new video related to blockchain, related in general to Bitcoin education, but it's the 12th video out of 15 related to explaining the blockchain. In this video, the topic will be exactly the blockchain to order the blocks. And I think is for the technology perspective is the most important presentation because it will discuss about the blockchain, and now we can discuss because we built with several other presentation all the steps in order to reach to discuss about the blockchain. Let's discuss, start with the disclaimer. This presentation is for educational purpose only. It is not a financial advice. I took the information from these two books, The Basics of Bitcoins and Blockchains, and Blockchain Basic, a non-technical introduction in 25 steps. The authors are Anthony Lewis and Daniel Drescher. I strongly recommend you to read both of the books in order to gain more and more knowledge on this fascinating technology. As you can see here, we started with the double spending problem, then we introduced the blockchain, we discussed technology like public key cryptography, a hash function, and then we went step by step from a centralized to a decentralized world. And we are now at part 12 and the step 8, where we have the problem how we order the block. Let's start with a summary as always. At this point, we have then transactions bundled in blocks, and bookkeepers agree on the order of blocks that are propagated around the network. We have therefore eliminated the role of third parties in creating of a third party in creating accounts, in maintaining and ordering the list of transactions. Furthermore, we have miners who are creating the blocks that contain the transactions. The miners are incentivized via block rewards and transaction fees. We have also introduced the difficulty adjustment that makes sure that programmed scarcity is kept despite the advance in technology and the increase of hash power. We know now that transactions are bundled into blocks, which are like pages in a ledger. But now the problem is, and this the main topic, how do we know what order the block should be? So how do we order the blocks? In a book, each page has a unique page number, and you know that the pages follow in an ascending order. But in a decentralized world, it is not the same, because while block 1000 is mined, and miners are starting to build block 1001, one sneaky miner can already start to mine block 1002. Therefore, instead of having each block a block number, what we have is a blockchain. And let's discuss about this. In the decentralized digital world, in fact, there is, let's start to discuss about causality and unpredictability, the topics that the time in a decentralized world need to have. In a decentralized digital world, in fact, there is no clock, no unique time. You cannot put the page that 45 is coming automatically after 44. So time has two characteristics: causality and unpredictability. I took this information um, from the article Bitcoin is Time. I also discussed about this in the videos Time in a Decentralized World. And it is the author is Dergigi. It's really great article. You can just Google it and say Bitcoin is Time, Dergigi, and you will find the article. So the time has two characteristics in a decentralized world: causality and unpredictability. Let's look at causality first. In the kidnapping world, to demonstrate that the person kidnapped was alive at a certain time, they were not showing a clock and a calendar because they could have been easily falsified. So everyone can falsify the number of the page. So they used newspaper of a particular day to demonstrate that the person was alive the day the newspaper came out. In fact, causality is the reason why cryptographic hash functions, now related to Bitcoin, are so crucial when it comes to timestamping documents in cyberspace. They introduce a causal relationship because it's not possible to create hash functions without having the document in the first place. We will discuss more in the details later, but keep the same link. So to in the kidnapping world, the kidnappers are using newspapers to prove. So they link something that already happened to be to the newspaper and the person being alive. So the person could not be alive before after this and showing this picture. This is causality. Now let's look at unpredictability. And the second is the second characteristic. In fact, with authentication by newspaper, kidnappers rely on something that could not have been predicted in advance. So time should also be unpredictable, because if you predict, then you can also make fake. And Bitcoin relies, in fact, upon two sources of unpredictability: transactions and proof of work. Just like nobody can predict what tomorrow's newspaper will look like, unless the people who create the newspaper, nobody can predict what the next Bitcoin will look like. You can predict transactions that are going to be included, because you can predict what transactions are going to be broadcast in the future. And more importantly, you can predict who will find the solution to the current proof of work puzzle and what this solution will be. Keep it in mind, we need causality and we need unpredictability. We need that the block is linked to something that happened in the past to prove that it happened later, and we need unpredictability. We need that no one knows as it happens which will be the hash function and which will be the solution. Now, let's discuss about the solution proposed by Satoshi Nakamoto. It's called timestamping. In fact, for the blocks ordering proposed this, it is not a new invention. Also, timestamping is again as a proof of work, as a public key cryptography, as digital signature, is not from an invention from Satoshi Nakamoto, but he was so wise to use this for the blockchain. In fact, Bayer, Haber, and Sornetta in 1992, they wrote, to establish that a document was created after a given moment in time, it is necessary to report events that could not have been predicted before they happened. In this paper, we propose a solution to the double spending problem using a peer-to-peer. This is what Satoshi said in 2008. In this paper, we propose a solution to the double spending problem using a peer-to-peer distributed timestamping server to generate computational proof of the chronological order of transactions. So he took also both proof of work from Adam Beck, Hashcash, and he also took the timestamping from Bayer, Haber, and Stornetta. And instead, each of having a block number like each page of the book has a page number. Each block refers to the previous block by its hash. Therefore, it's not possible to create a new block without knowing the hash of the previous block. In this way, Satoshi Nakamoto brilliantly found a solution to recreate the time in a decentralized world. Meaning, if you have block 10, this block 10 will have a hash because the data are agreed. There is a hash function. You cannot build block 11 without this hash. And this was the elegant solution found by Satoshi Nakamoto to recreate time in the decentralized world. And in fact, creating a new block involves the following. Now that we have reached the step of explaining the blockchain, we can be more specific on the on the process of creating a new block. What exactly mean creating a new block? Involves the following steps. Firstly, get the root of the Merkle tree that contains the transaction data to be added, and I will come back to the Merkle tree later. Then create a hash reference to the header of that block that will be the predecessor from the new block header point of view. So in order to create the current block, you need to have the hash reference of the previous block. So the previous block has to be created. Then obtain the required difficulty level that is clear for everyone. Will be the difficulty level is the same every 2 weeks, and then it change according to the average time effectively spent, as we saw in the difficulty adjustment. Then the person is getting the current time. Create a preliminary block header that contains the data mentioned in point 1 to 4, solving the hash puzzle for the preliminary block header, and then finishing the new block by adding the nonce that solves the hash puzzle to the preliminary header. Let's look on example. In this figure, in fact, we can see that the hash puzzle that needs to be solved when adding a new block to the blockchain data structure. It shows the data of the block header whose hash value has to fulfill for a given the given restriction or difficulty level respectively. The difficulty level is part of the block header and hence is part of the block's hash value. This ensures that no one can bypass computational cost of the hash puzzle by arbitrarily reducing the difficulty level. So adding both the previous hash and the difficulty adjustment, and that the number should be lower than the difficulty adjustment, it makes sure that the block 10 was created after block 9, because otherwise you cannot create block 10 without the hash of block 9. So block 9 should be created. And secondly, with the difficulty adjustment, it's clear that you spend bits, so you spend energy, you spend electricity. There is a proof of work in order to find this block. And regarding validation rules, each block has to fulfill the following ones. It must contain a valid hash reference to the previous block. It must contain a valued root of a Merkle tree containing transaction data. It must contain a correct difficulty level. Its timestamp is after the timestamp of its preceding block header. It must contain unknowns. The hash value of all the 5 pieces of data combined together fulfill the difficulty level. So it means that all of these 5 do the hash. It should be less than the target number. Let's now, in this way, now we have a chain of blocks. You can see here block 10, block 11, and block 12. And hashing block 10, you have the hash for in block 11, and the hash of block 11 appear in the data of block 12. So we have a blockchain where each block is linked to the previous one. We have said that the block contains the root of the Merkle tree Merkle tree representing all the transactions and not the transaction themselves. It's not that there are all the transactions are in the block. There is the Merkle tree, and this is the representation of all the transactions. Now let's look how it works. In fact, it is an efficient way to list all the transactions. Let's say for simplicity that a block has 8 transactions. Every transaction will have a hash, and they will be combined in a couple of hashes to make a new hash. So the hash of transaction 1 and the hash of transaction 2 will be combined and hashed, creating the hash T transaction 1, 2. In the same way, we have the hash of transaction 3, 4, 5, 6, and 7, 8. Then the hash of T1, 2 will be combined with T3, 4, creating T1, 4, and the hash of T5, 6 will create the hash of and combined with the hash of T7, 8 will create the hash T5, 8. At the end, the hash of transaction 1 to 4 will be combined with the hash of T58 will be hashed, and they will create the hash of transaction T18. And this can work if you have 8, 16, 32, 2000, and how many you can have. But this is the way how you create a Merkle tree. And the final hash will be the value that appear in the block, in the respective block. Every change, very important, every change made in a block that is already part of the blockchain will be detected and will have an impact. And there are 4 cases: changing the content of transaction data, changing a reference in the Merkle tree, replacing a transaction, or changing the Merkle root. In the picture, we can see, for example, an example of 2 blocks who contain the Merkle tree of 2 transactions each. And we can see that in case the content of transaction is changed, for example, T2, and then the hash connection with R2 will be compromised. In the same way, if we change a reference in the Merkle tree, for example, R2, the hash connection between R2 and R12 will be also compromised. Similar outcome will happen in case we replace a transaction. For example, we replace T2 with T5. The hash connection between the new transaction T5 and the old reference T2 will not work anymore. Last but not least, in case we change the Merkle root, for example, R1, 2, the connection between the blocks will be compromised because the hash reference of the previous block will not be the same. And let's move on for the next example. And in this figure, we can see that instead how we can change the data orderly. Previously, I showed that it's not easy to cheat or to recreate transaction because it will be clear that the hash connection is not the same. In case you want to change the data orderly, then if we consider changing or updating some details of transaction 2, for example, T2, we have to subsequently update the whole sequence of hash reference R2, R12, B1, and B2. And this means that all hash references, starting with the one that directly points to the manipulated data, ending with the hash reference that points to the most recent block header, as well as all hash references between them. It's like a chain you have to change every single part of the chain. This is quite an elaborate task, and it is an elaborate process on purpose. It's done on purpose, and it's a genius how it's done because all of this work is necessary to keep the whole blockchain data structure consistent to keep its integrity. It's very computational energy requiring in order to change the blockchain. All other attempts to change or manipulate data are part of blockchain data structure will cause invalid hash references because in order to change T2 transaction 2 you have to change the whole chain. And if you don't do orderly, then in turn will invalidate the whole data structure. That's also that thing. That's it for the presentation today. I think it's the most important presentation really to explain how the blockchain works, and it's possible now that we already discussed about proof of work, difficulty adjustment, and hash functions. So you can see here the great solution that Satoshi Nakamoto found, not invented, because he took he took other existing technology, but he was so genius to choose the right technology. And that's it for today then, and remain just 3 presentations related to blockchain. I hope you enjoyed and see you in one of my next videos. Bye.